Last week, we learned that atoms want to be happy, and they do that by having a complete valence shell. They want to have 8 electrons in the outermost shell, which is the configuration of noble gases. When metals and nonmetals react, they form octets by transferring electrons, forming ionic compounds. When nonmetals react, they form octets by sharing electrons, forming covalent compounds. This is an overview of what we will look at for the remainder of Chapter 6. Given the name of molecular compounds, write the formula, and given the formula, determine the name. Then draw the Lewis structures, and using electronegativity, determine the bond polarity. Predict the three-dimensional structure of a molecule. And lastly, use the three-dimensional structure of a molecule to classify it as polar or nonpolar. When naming a molecular compound, the first nonmetal in the formula is named by its elemental name. The second nonmetal is named by using the first syllable of its name followed by IDE. When a subscript indicates 2 or more atoms of an element, a prefix is used in front of its name. Let's look at NO2, NO3, and NO as examples. For NO2, the first nonmetal elemental name is nitrogen. The first syllable of the second nonmetal plus IDE is oxide. Since there are 2 oxygen atoms in the molecule, we add the prefix di to oxide. Therefore, the name for NO2 is nitrogen dioxide. Following the same rules, NO3 is nitrogen trioxide. When there is only one atom, the prefix mono is usually omitted, so NO is nitrogen oxide. One exception to this rule is carbon monoxide, which still uses the prefix mono. Here are some examples of common molecular compounds. For practice, block the column name and identify the formula using the name. Also, you can block the formula and derive it from the name. Pause this video and attempt this example. First, write the symbols in order of the elements in the name. The first nonmetal is phosphorus, and the second nonmetal is oxygen. Second, prefixes denote the number of atoms of that element in the molecule. So diphosphorus denotes 2 phosphorus atoms in the molecule, while pent in pentoxide denotes 5 oxygen atoms in the molecule. So the formula for diphosphorus pentoxide is P2O5. Here's a nice flowchart for naming ionic and molecular compounds. Use this flowchart as a study guide and try to commit it to memory. Note how the naming is similar for ionic and molecular compounds. They both start with the metal name or the first nonmetal name, plus the nonmetal name or the second nonmetal name plus IDE. 2 main differences that are for ionic compounds. Roman numerals denote the charge for multivariable charges, while for covalent compounds, prefixes denote multiple atoms of the same element. You can represent molecular compounds as Lewis structures, which show the valence electrons in molecules. A hydrogen molecule forms as the atoms of hydrogen move closer, and the positive charge of the nucleus attracts the electron of the other atom. The molecule has a shared pair of electrons that form a covalent bond to give each atom a noble gas arrangement of helium to each hydrogen atom, which is more stable than individual hydrogen atoms. Given the molecule F2, we have 2 fluorine atoms. From the periodic table, fluorine has 7 valence electrons. The shared electrons or bonding pairs are shown as 2 dots or a single line between atoms. The non-bonding pairs of electrons or lone pairs are placed on the outside. The number of electrons a non-metal atom shares and the number of covalent bonds it forms are usually equal to the number of electrons it needs to achieve a noble gas arrangement. So fluorine shares 1 electron, so it usually forms 1 covalent bond. In addition to hydrogen and fluorine, there are 5 other diatomic molecules, which exist as 2 atoms of the same element covalently bonded together. One mnemonic device to help you remember them is hydrogen and oxygen form clear brittle ice. Each word in the sentence represents a diatomic molecule. You can also remember that all of the 7 diatomic molecules end in GEN or INE. So nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, and iodine. Lastly, they almost form a 7 on the periodic table as indicated on the image. To draw the Lewis structure for methane, CH4, we start by drawing the Lewis symbols for carbon and hydrogen. Recall that the number of dots is the same as the valence electrons, which can be determined by the group number. Carbon needs 4 electrons to complete its valence shell and attain a noble gas electron configuration for neon. Since hydrogen has only 1 electron to share, carbon will bond with 4 hydrogen atoms. Here are examples of Lewis structures for common molecules: methane, ammonia, and water. Use this for practice using the rules we have just looked at. In addition to single bonds, when atoms share a pair of electrons, atoms may share 2 pairs of electrons, which is called a double bond, as in the molecule for oxygen. They may also share 3 pairs of electrons, which is called a triple bond, as in the molecule for nitrogen. Pause the video and draw the Lewis structure for carbon dioxide, CO2, which has carbon as a central atom. You are given carbon dioxide and you need to draw the Lewis structure. To do that, you need to know the total number of valence electrons which are involved in the chemical reaction. First step, determine the arrangement of atoms. Since you are told that carbon is a central atom, place the 2 oxygen atoms around carbon. Step 2, determine the total number of valence electrons. Remember, the group number is the same as the valence electrons. So carbon, which is in group 4A, has 4 valence electrons, while oxygen, which is in group 6A, has 6 valence electrons. Since we have 2 oxygen atoms and 1 carbon atom, the total number of valence electrons is 16. Step 3, place a pair of bonding electrons between each atom and the central atom. You have used 4 electrons. Now 12 electrons remain. Step 4, place the remaining electrons to complete octets, starting with the atoms around the central atom. After placing the remaining 12 electrons around the oxygen atoms, note how while the oxygen atoms have complete octets, carbon only has 4 electrons. To complete octets for carbon, use the lone pairs on oxygen to form double bonds between carbon and oxygen. Now all 3 atoms in carbon dioxide have complete octets, and we have used up all the valence electrons. There are a few exceptions to the octet rule. As we've already noticed, hydrogen is happy with 2 electrons in its valence shell, so it doesn't need 8 electrons. Also, nonmetals in period 3 and beyond can have more than 8 electrons in their valency shell. Examples include phosphorus, sulfur, chlorine, bromine, and iodine. Just use the total number of valence electrons to determine Lewis structures involving these atoms. Up to now, we have covered ionic compounds and naming molecular compounds, as well as drawing Lewis structures. Next, we will use this information to determine the polarity, shapes, and attractive forces between molecules.